Cloud. It changed your voice. Hello, welcome. We are trying to do 1.3, number 6. Okay, so in order to do 1.3, number 6, we first need to understand what in the hell they're getting at, which I think is really the crux of this. So the author likes these questions. I like these questions. So this kind of theme will reoccur. They're asking which numbers C give dependent columns, so a combination of columns equals 0. Everybody with me on that? Mm-hmm. Probably not. Okay, good talk. So let me consider, I'm going to consider this one with lots of 1s in it first, right? So I'm going to look at this guy, and I'm going to think to myself, okay, self, what they mean by dependent columns is that there's going to be some combination, right, of, well, I need 3 scalars. So I would normally use A, B, and C. That seems a little problematic here. I'm going to use A, B, and D. Just because. Pretty good with that. So they're saying that if they're going to be linearly dependent, there are 3 scalars, so that A times the first column plus B times the second column plus D times the third column are going to equal the 0 vector. You guys with me on this? This is what it means to be linearly dependent. So dependent implies that there exist A, B, and D in R, not 0, right? So R take away 0 with this. And this notation is just a little bit sloppy. You guys with me on that? The reason this notation is a little bit sloppy is that one of them could be 0 as long as the others aren't. Really, what I need is not all 0. So I'm going to revise that a little bit. Does that distinction make sense? If I was requiring that they all be in R less 0, then none of them could be 0, where the actual requirement is that not all of them can be 0. Does that make sense? None versus not all. Like, not all of you are Zach, but one of you is. Does that make sense? Okay. All right. So I have A, B, and D, not all 0 with this. Okay, so now let me kind of examine about A, B, and D. You guys see that? So I think what I'm going to find here is from my from my second coordinate, I can see that A plus B has to be 0. You guys all on board with that? So that's kind of the y coordinates tell me that A plus B is 0. What does the z coordinate tell you?
B plus D is 0.
Good. Very nice code. Okay, what does the x coordinate tell me? Because that one's a little bit weird. Everybody got me on that?
1 plus C is 0?
Kinda. So remember that's A times 1. So A plus, and then this one's going to be D times C. It's going to be 0. You guys all on board with this? Mm-hmm. Okay, so if I rearrange those a little bit, this one, the y's tell me that a is minus b. The z's tell me that b is minus d. So my whole linear combination thing becomes, well, I just learned that I can cross a out and write minus b. And I can cross d out and write minus b. You guys see all that? Put it kind of on board here. Okay, so I think then I probably know some stuff about what C can be. So one way I could see this is I could factor a kind of a B out of this whole thing. Another way I could do this is I can look at my equation here. I don't really care which approach you take. The equation approach is probably as easy as anything. So this would tell me that A is minus B, right? And then I have minus B times C is 0. This would give me what? If I factor a minus B out, I get 1 plus C is 0. You guys all with me on that? You all are very quiet and your cameras are off. So I don't know whether you're with me or confused or bored or where you're at. Do I need to do something amusing? Shall I juggle?
Do a little dance. I'm entertained. Continue.
Excellent. It is my goal to entertain and educate. All right, so what do I get out of this? What does that mean? If I have two things multiplied together equals 0, what can you tell me?
C is 1.
Yeah, either C is, well, close.
Well,
-1.
negative
1
1,
of
yeah.
0.
Yeah, Karen, thank you for the algebra support. Yeah, one of the two things is 0, right? So this would tell me with the 0 product rule, either C is -1 or B is 0. You guys see that? So C is -1 is an answer. What about B is 0?
It can't be 0 because then D and A would add to not 0 vector. Like
maybe. Let me think about, so if B is 0, I know that B is minus D.
Oh.
You guys see that? So if B is 0, what's D?
-0.
Yeah, D is -0. So D is also 0. And what do I know about A?
Also 0.
Also 0.
They can't be 0.
So either C is -1 or A, B, and why did I write B twice? Guys. B is 0 implies B is 0. Thank you, Joe. Okay, so either C is -1 or all three of them are 0. You guys see that? But my requirement was that they not all be 0. So this thing doesn't work. You guys all see that? So in the end, for the middle one, I end up with C is -1.
Oh, so if D is equal to -B and C is -1, that means you'd have non-0 for your topmost part of your 0 vector. So like
Okay, so hang on, go back through that again, slow, Jacob.
So if D is oh, you know what? I just realized A is also -B as well. So never mind.
Yeah, so in the end here, right, I found C as 0. That doesn't tell me anything about A, B, and D, which is kind of the beauty of this. I could go find them.
Well, I was just thinking like, because if D is negative B and C is negative 1, that means C would come out positive. So
Yeah.
but then A is also negative B, so it's negative 1, so it cancels.
Yeah, so essentially the three vectors I'm looking at then are 1, 1, 0. And so we have A times 1, 1, 0 plus B times 0, 1, 1 plus C times, oops, C is a shit choice, D times minus 1, 0, 1. And these I can see are pretty clearly dependent, right? If I take this one, subtract that one, right, then I'll get a 1 and a minus 1. And if I add that one, so if I do add this one, subtract this one, and add this one. You guys see that? I get out the 0 vector. So that's just me checking, right? You guys following? I'm trying to make my notes a little bit more clear. Any questions on that? So that was essentially part B, right? So if I want to go through and do that with A, you guys with me on this? There's some kind of more eyeballing stuff you can do. So on part A, right, I can see that if I'm going to get 0 in the top from adding multiples of these three vectors together, let's see. So I need just that guy. So if I was going to do this, I'd probably be a little lazier. So I'd look at this thing and say, okay, so if I'm going to get A times 137 plus B times 124 plus 0, 1, C to equal the, oops, D times 0, 1, C to equal the 0 vector, I'm going to look at that x coordinate. I'm going to say A and B have to be opposites of each other, right? So I'm going to kind of think about taking 1, 3, 7 and subtracting 1, 2, 4. You guys see that? It's the only way I'm going to get that 0 in the top or some multiple of this thing. So out of that, I'm going to get a vector that's 0, 1, 3. You guys see that? Does that look familiar? Well, that looks an awful lot like that guy. You guys see that? So C is 3 is going to do this for me. Does that make sense?
Joe, so right now I was like looking at it and I kind of solved it with some other method, and I also got C equals to 3.
What's your other method?
So I did it as a matrix, you know,
Mm-hmm.
like do the cross multiplication of these and put them equals to 0.
You mean you calculated the determinant?
I don't know exactly.
You did the like cross product thing to it, right?
Yeah.
Yeah, that'll work too, but we don't know why yet.
All right.
But that works. So if you want to do that, like if you know how to calculate a determinant, you guys know how to calculate a 3x3 determinant. So an alternate approach would be to take the determinant of this thing get, let's see, it's 1 times the determinant of 214C minus 1 times the determinant of 371C plus 0 times some garbage. I don't know if you guys all know how to do this. Does everybody know how to do this, or is this foreign to some people who maybe didn't take Calc 3? Where you at?
Well, not everyone's here, but since we have some high schoolers as well, I'm going to assume not everybody knows how to take the determinant here.
Okay. So for those who don't know how to take determinants, we're going to learn this later. For those who do know how to take determinants, you can use this now and cheat. How about that?
All right.
If you want to go to the section about determinants in the book and learn how to do it, don't. Go on YouTube and find somebody who will teach you how to do a determinant. Because the section in the book is a little bit like abstract, and it might be a little over your head right now. Because, yeah, it's later for a reason. But if you know how to do it, go for it. You just set the determinant equal to 0 and solve. And we'll talk about the determinant.
I was just about to ask why that works, and then you just said we don't know yet. So
yeah, it works because it works.
yeah.
Right now. Later I'll give you a better reason, but for right now it works because it works. If we looked at part C of this thing, you guys see that? Part C might not be doable. Do you guys see that? I'm kind of coming up with an equation at the ends of these, and it's pretty possible that that equation might not have any solutions. That same thing is pretty possible here. One way we could do this is we could we could think about the fact that 2, 3, and 1, 3 are probably not gonna cancel conveniently, right? But if I try to get these to combine to 6 so I can cancel with that guy, I'm gonna have to use kind of equal parts of these, and that's not gonna cancel this 5.
Yeah.
Fiddle around with this a little bit. It's not so bad, but you might end up with an equation that doesn't have a solution. That's kind of what they mean by they're maybe always independent for C's not 0. It should be noted that if you put a whole row of zeros in, that does in fact satisfy their requirement here. You guys see that? Mm-hmm. In this process, it shouldn't be a huge surprise that you could get a couple of solutions in one of these if there were a couple appearances of C. This one's actually a little surprising because C not 0 probably doesn't solve this. You guys kind of on board? Fiddle it out. If you find anything interesting, hit me up.